Hey there, everybody. Welcome back. This is our final video for 13.8, and this will be the last section before our test on Chapter 3. 13.9 is on Lagrange stuff, and we will do that later on. It won't be on the exam. So let's take a look at this. We'll do the finding the 13.8 is on the extrema. In this video, our final video, we're going to find absolute extrema. So there's a theorem that is going to be pretty handy. If f of x, y is continuous on a closed bounded set D in R2 or 2 space, then f attains an absolute max and an absolute min somewhere in D. Why is that helpful? Well, we know the critical points are either along the boundary or inside of it. And since it's a closed bounded set, there's got to be absolute max and an absolute min somewhere, since we've got the entire domain enclosed in the set. So our procedure to find absolute extrema in closed bounded sets, we need to find the interior critical points. I will be calling them IC points on the next page. That's not common lingo, but save some time. Then we will find the potential boundary points that will be critical points. When I mean potential, it's not a physics term. I just mean the boundary points where we could have an extrema. They are potentially maxes or mins. Finally, we will evaluate f of x, y at all the points that we found in 1 and 2. To find the largest and the smallest will be our absolute max, and the smallest will be our absolute min. So I got a nice problem for us set up. Find the absolute extrema on the rectangle that goes from 0 to 3 along the y-axis and 0 to 2 along the x-axis, for f of xy equals 12x plus 6y minus 6xy plus 4. I took my two partial derivatives already. The partial derivative with respect to x is 12 minus 6y. And we see that gets us y equals 2. The partial derivative with respect to y is 6 minus 6x. We find that gets us x equals 1. There is only one interior critical point, and I marked it on the map at 1, 2. I drew a little map to show. Now we want to look along the boundaries. The boundary conditions along A, B, C, and D are different. So let's just look at each side one at a time and see what those boundary conditions tell us. Okay. So along A, the lower side, y equals 0. So f of x 0 is really just a function of x. So I called it a of x. And when I plug in 0 here, this zeroes out, this zeroes out. So we just get 12x plus 4. Okay, that's what I'm going to be doing throughout these things. When I'm doing it, I'm going to be plugging in constants for these. And you can check the math with it when we do it, but I just showed you there. 0, 0, we're left with 12x plus 4. If I take the derivative, it's 12. It's positive the whole way, which means the only spots we could possibly have extrema at would be the endpoints. So 0, 0, and 2, 0. Let's look along B. Along B, x equals 2. So if I plug in 2, again, we're using this function up here. It now just, we plug in 2 for x, it now just becomes a function of y. You can double check to see that this function would be 28 minus 6y. The first derivative is -6. Again, it's not 0 anywhere. So there are no critical points on the inside of this line, or this line right here. It can only be at the endpoints. So nothing along this line right here, nothing along this line right there. This point here is 2, 3. This point here is 0, 3. Let's check C and D. Along C, y stays constant, it equals 3. So if I evaluate my function up here at y equals 3, I get a function in terms of only of x where it's negative 6x plus 22. And when I have negative 6x plus 22, we take the derivative, it's negative 6. Again, it's not equal 0 anywhere. So there's nowhere along the line on the inside that can equal it. Again, only the endpoints. And so far we have one initial condition, or sorry, one interior critical point. We've got 4 boundary points that we can check. Let's see if there's somewhere along line D that we can check also. Along D, x equals 0, and our equation is just becomes a function of y, 6y plus 4 when we zero out the x's. The first derivative is 6. It's not 0 anywhere. We have no interior critical points anywhere along D either. So we've only got our 4 endpoints and this point right here. The absolute extrema are there somewhere. So what we do is I made just a little table and I evaluate each of the points. If I plug in 1, 2, I get 16. If I plug in 0, 0, I get 4. If I plug in 2, 0, I get 28. 2, 3, I get 10. And 0, 3, I get 22. The absolute min occurs at the smallest value of 4, which is 0, 0. So the absolute min is at 0, 0, and it equals 4. The absolute max is at 2, 0, and it equals 28. Feel free to pause this and double check the math if you need, but I didn't want to bore you with the blah blahs. That's it for 13.8. Peace.